In many DE courses, boundary value problems are a topic that appears at the end of the course. A lot of courses include a brief introduction to, say, the heat equation or the wave equation. And in the course of solving those, students get introduced to Fourier series. And so I want to show you a little something I do after they've seen the idea of a Fourier cosine expansion, something that kind of livens up the presentation and shows them an important application of Fourier series that they don't normally see in a DE course. So at this point, when I do this, here's what the students know. They know that one of the great discoveries of 19th century mathematics was that you can decompose functions and express them as sums of sines and cosines. And any reasonable function defined on an interval, I'm thinking of f of t as a function of t time. A function defined on an interval from 0 to capital T can be well approximated as a finite sum involving cosines, like you see there, if you choose those coefficients, A0, A1, et cetera, correctly. And so to illustrate, on the left, there is some random cubic polynomial I made up, the graph of it. On the right is the Fourier cosine approximation using just one lousy term, namely the constant A0. So that blue line there is the optimal approximation of the function if that's all you have to work with is a constant. If you're willing to throw in cosine pi t in this case, since we're working on the interval 0 to 1, on the left you see the optimal approximation using cosines. If you're willing to throw in cosine 2 pi t, on the right you see the best approximation. And now in the case, if you're willing to throw in 5 cosines up to cosine 5 pi t, you get what you see there on the left, assuming you've chosen the a sub k correctly. And on the right, you see what you can get if you throw in everything up to cosine 10 pi t. So the students have seen this idea at this point, and they know that a piecewise smooth function can be well approximated as a sum of cosines in that form, where the a sub k's, the coefficients, are computed using that integral. So at this point, we've developed Fourier series. Maybe we've solved the heat equation with them, but I like to do this to give them another point of view on these things. And they know that as you increase the number of terms in the sum, the function, the sum Sn converges to f in a quantifiable sense. Well, here's a point of view that often doesn't get mentioned in a course like this. Cosine k pi t over capital T, it's a cosine, it has a frequency, and it's easy to work out. It's k over 2t hertz, if we're thinking of t as time in seconds. And that decomposition of f into a Fourier cosine series, it's a decomposition of f of t into a sum of cosines of different frequencies. It's telling us how to synthesize a function of time using cosines of various frequencies. And the a sub k tell us exactly how much of each frequency we need to synthesize f. So to illustrate, in red there at the top is some other random function I made up living on the interval from 0 to 1. And I compute the first few Fourier coefficients, cosine coefficients of this thing. And I want to point out A0 is the 0 hertz contribution in the Fourier cosine series. That's the constant term. A1 corresponds to, since we're working on the interval from 0 to 1, A1 corresponds to a cosine that lives at a frequency of 1/2 hertz. A2 corresponds to 1 hertz. A3 corresponds to 1.5 hertz. Those coefficients are telling us how much of each cosine of each frequency we need to synthesize the function f. And you can plot this information as follows. On the left, I show the function itself as a function of time. That's the f of t up here. On the right, I plot the Fourier cosine coefficients, or rather their magnitudes, their absolute values. And I plot them as a function of the frequency to which each one corresponds. So for example, this highest one here, that's A3, it corresponds to 1.5 hertz. And so that's the dominant, you could say that's the dominant frequency in this signal. And of course, that corresponds to this cosine 3 pi t term up here. And then the t minus t squared contributes a little bit of garbage here. And you see that from 2.5 hertz on up, there's essentially no such frequencies in this signal. So this point of view of the Fourier cosine series, or really any Fourier series, is telling you how to decompose a function of time into different frequencies. But the problem is, so this is what I just iterated. The AKs quantify how much of each frequency is present. The problem is, when you do this analysis in a computer, the signals you get are not functions of time. If you're trying to do this to an audio signal, for example, you don't get a functional form for the signal. You get samples of the signal. Say, like a CD audio signal is sampled 44,050 times per second. You get measurements of the function, not the function itself. So that's illustrated in this picture right here. In red is the, if you will, the real world analog signal out there. And the black dots represent samples of this signal in this case, every 10th of a second. So in this case, the signal is sampled at time 0.05, 0.15, 0.25, 0.35, et cetera, up to time 0.95, 10 samples taken every 10th of a second. That's what we have to work with when we want to do this Fourier cosine analysis. And that means we can't, the question is, how do we do the integrals? Well, here's what we're going to do. We're going to assume that the sampling takes place at equispaced time and there are n samples over an interval from 0 to capital T. And so those are the times at which the signal has been measured. We're going to we don't get the function f of t, we get this vector here that represents the sampled values of the signal exactly as in the last slide. And that's the data we have to work with to try to compute these Fourier cosine integrals. How do we compute the integrals of this function using the sampled data? Well, we're going to use the midpoint rule straight out of Calc 2. So the midpoint rule tells us how to approximate an integral using essentially sampled function values. So in red there is the true analog signal, if you will, and we'd like to compute its integral. The black dots represent the sampled values. The yellow rectangles, well, we compute their areas as an estimate of the integral of the function g of t here. We're going to apply that to compute the Fourier cosine integrals. So that integral right there, we don't have the function f of t, we have its sample values at equispaced times. We replace the integral with the midpoint rule approximation. And it looks like this. A sub k is the true cosine coefficient. I use capital C sub k to indicate the result of applying the midpoint rule to this function, right, to this integral right here. And the f sub j's here are the sample values of the signal at those periodic times. We can compute the C sub k if we have the samples f sub j. Now, the question is, how good is the approximation? Well, you know, if you've done any, I mean, it's the midpoint rule or a midpoint Riemann sum, if you will. You know that if the function is highly oscillatory, the midpoint rule isn't going to be accurate unless you take a lot of samples. Well, that's the case here. As k gets larger and larger, we're trying to estimate an integral that's more and more oscillatory. So I would expect that this approximation breaks down when k is large. That is correct. And you can analyze that. I'm not going to do it here, but you'll find that the approximation is reasonable if k is up as large as n minus 1. In other words, you can estimate the Fourier coefficients a0, a1, a2 up to a n minus 1 with some reasonable accuracy. However, as soon as you get to trying to estimate a sub n, well, you find that c sub n, our estimate based on the midpoint rule, c sub n always equals 0, no matter what, due to certain symmetries in the midpoint rule. And regardless of what the nth Fourier cosine coefficient is. So, and once k is larger than n, the process breaks down completely, and you can't estimate those Fourier coefficients once k is larger than n. And so we're going to restrict our attention to using this to estimate the Fourier coefficients corresponding to a0 to an minus 1. Well, okay, so this corresponds to a frequency range in the signal from 0, that's what a0 quantifies, up to an minus 1, which quantifies the frequency n minus 1 over 2t hertz if we're measuring time in seconds. And if you're familiar with this stuff at all, you recognize that as essentially the Nyquist frequency in this process. But I'm not going to go into that. But those we can estimate. We can now do Fourier cosine analysis on sampled signals. Replace the integrals with the midpoint rule. That formula there that we're going to use to do this analysis, it is up to a minor change of scale, what is called the discrete cosine transform, and it forms the basis for example, JPEG image compression. So let me show you an example of applying this. So at this point, I show this to the students, and I have them go collect audio signals on their phones. They can sample audio signals on their phone and do the analysis that I've just shown you. I'll show you an example of what I did on my phone. So what you see there on the left is a graph of an audio signal that I obtained from my iPhone by whacking a big metal dinner gong I have in the kitchen. It makes the most pleasing sonorous sound when you hit it. And so I sampled the audio signal from that thing for 3.33 seconds, sampling it at 16,000 samples per second. So a total of about 53,000 samples. That's our N here. In the right panel is just a close-up of the audio signal for 1/100th of a second. And so what I would like to do is take this audio signal and do Fourier cosine analysis on it using the discrete procedure I just showed you. The values, so what I do is I compute all these C coefficients, which quantify how much energy or how much of each frequency is present in the signal. And I plot the magnitude of these Fourier cosine coefficients as a function of the frequency to which they correspond. And that's what this graph here on the lower left panel is. The frequencies correspond to 0 to 8,000 hertz. And I plot the magnitude of these Fourier cosine coefficients. In the right panel, I zoom in on the interval from 0 to 2,000 hertz, because that's where most of the action is in this signal. And you can see here that there are certain very peaky dominant signals in this audio, or frequencies in this audio signal. Those are the frequencies at which this big round gong vibrates. And so the students can do their own, can sample their own audio signals and do this analysis. Also in the website for the book, the Simeo textbook I wrote, I put this signal on there. I put in some data from that Bryan collected concerning the vibration of a spring mass system, so they can analyze that to find the characteristic frequency at which the system vibrates. And from that, you can infer certain parameters about the system. I put in some data from sunspots over the last few hundred years. They can analyze that to find that the sunspots have a very dominant 11-year cycle. So they can do all kinds of frequency analysis. And so, as I said, it's clear what frequencies dominate the audio signal from the gong. And from that, if you had a model of how a metal plate vibrates, you could use that to infer parameters about the plate, density, stiffnesses, stuff like that. The computation is a large one. If I have 53,000 data points, it turns out that the amount of computation is proportional to 53,000 squared. So it's a lot of computation, but almost all the software that that for example is supported, that the book supports, Maple, Mathematica, MATLAB, and Sage, all have routines for computing these coefficients quickly. It's all based on the fast Fourier transform. You can do this with a fast Fourier transform, which is arguably one of the most important algorithms of the last 100 years. So I have the students do this and analyze their own audio signals, and it just puts a fun spin. So they have some real world data to hang the idea of Fourier series on, and a lot of them are going into engineering, so they need to know this idea that you can decompose signals into constituent frequencies and figure out all kinds of stuff about them. They can use their own cell phones, which every single one of them has now, to analyze audio signals. And this kind of frequency analysis, I mean, it's not an overstretch to say our civilization would collapse without this now. I mean, almost all the technology we rely on uses this kind of Fourier analysis using cosines or some other basis. So that's something I like to do in my class to sort of wrap up Fourier series for them. So I'm open to questions.
Kurt,
Yeah.
How do the students get the phone signal onto the computer for the?
Oh, they just email it to themselves. That's why just email it to yourself.
Oh, and then it's in a format that MATLAB or Mathematica or any of those other platforms can read.
Yeah, well, you have to. It depends on. Yeah, there's a little bit of a game you have to play where you have to. I mean, depends on what software you have on your phone, how it will store the audio signal, and then MATLAB is the most flexible one for reading in audio signals in various formats. I've forgotten. Mathematica can read in a variety of formats. Maple seems more restrictive than some. So you have to play a game where you match what can your phone do versus what software do you have.
Thanks.
Kurt, Tim Pennings here. What are some kind of practical reasons why a person would want that information? Where would that be helpful in industry, for example?
In the frequency analysis?
Yeah.
First of all, the one the students could get their hands on right away is Bryan Winkle's vibration data for a spring mass system. If you can pick out the dominant frequency in that signal, you can infer the spring stiffness, for example. And I've used it in industry for non-destructive testing, where we were once we were doing non-destructive testing on these. It's a long story, but they were railroad ties, metal railroad ties that you put in the bed of the railroad. And we were having problems with these things cracking and failing. And so this is a common procedure in mechanical engineering. If you want to know the structural properties of something, you hit it with a hammer, and then you listen to it or monitor its vibration. And from that, you can infer things like, is there a crack in it? So that's one place where I have actually used this in industry. That's cool. One example.
Okay.
Go ahead.
There was a paper that was really popular back in the mid 80s, as I recall. I was in grad school. Can you hear the shape of a drum?
So this would be, if you monitored the shape of, the gong I hit. The question is, what if I had perfect data and I could see all the frequencies present in the gong? Could I tell that it's a disc? It's a disc and it's not a square. Could I infer how big it is if I knew something about its material? It's exactly the kind of thing we're talking about.
Yeah, very neat. Thank you.
Scott, did you have unmute yourself? Did you want to?
Right. Yes, thank you. What was the class where you start this project?
So we have two differential equations classes that most students need to take. We're on a quarter system, so two quarters, because we're mostly engineers. This is at the end of our second course in differential equations, where they're getting exposed to about 2.5 weeks of boundary value problems. They get basically a taste of Fourier series and the heat equation. So this is what I'm doing exactly this week. I hope to do this project Thursday with them.
Very good. Thank you.
Anyone else?
There's a question in chat, Kurt.
Oh, there is? Oh. Let me pop it open. Oh, I just lost the chat. Where'd it go? What was the question? There it is. Is this related to the furnace problem?
There's one above it too.
Is that in the book? You mean the blast furnace problem? Is that, if that's the one? Yeah. No, it's not. Other than that, no, actually, I'd say it has no relation whatsoever. Other than that, you solve the heat equation with, you can solve it with Fourier series. And this is Fourier series, but they're really no particular relation between them. Although I did have students work on a non-destructive testing procedure using the heat equation, the blast furnace thing that came out of some stuff I had done, where they had to estimate the wall thickness of a blast furnace. And there was some Fourier analysis there, but it played a lesser role. So I guess in some ways it might be related. Yeah. Anything else?
Someone else asked, why use the DCT and not the DFT?
Oh, you can use the DFT. The reason I like the DCT is because it's real valued. Cosines have a easy, and it does, cosine k pi t has a well-defined frequency. If you get into the DFT, say with complex exponentials, then you've got e to the IKT and e to the minus IKT, and they're both frequency k over 2, and so you have to talk about this thing called conjugate aliasing, and it's just more complicated. Cosines are just really straight ahead and simple. That's why I do those. Also, the DCT forms the basis for JPEG image compression. So if I want to give them a project on like baby JPEG, I can use the DCT. They already know what the DCT is. But you could do the DFT. That would be, I mean, in some sense, that's more elegant. It's just I usually don't have the time. Anyone else? Well, thanks, everyone.